Hey guys, welcome back to the USACO walkthrough. It's Andrew here, back with another upload. And first off, I'd like to just thank you guys for the massive support I've been getting lately. I think we went up quite a few subscribers, and our view count increased quite a lot. We are almost at 5.5k, and this is, at the time of recording this. I'm recording this on New Year's Eve, so this is going to be the last video of 2021. And 2021 has just been crazy. The channel grew a lot in support and popularity, and I can't thank you guys enough for that. So without further ado, let's just get into the video here. Today we're going to be tackling the problem in the 2016 silver contest. It's going to be problem 3, closing the farm. So let's get into it. Okay, so let's just start reading here. So I'm not going to read the entire thing, but just to give you guys a general gist of it is that we have N barns connected by M bidirectional paths, meaning that we can access both barns that one path connects. So we have N bidirectional paths connecting N barns, and this is going to form some sort of like web of barns and paths, and this is just going to be described by a farm simply. So to shut the farm down, FJ is going to plan to close one barn at a time, so he's going to close it down. And when a barn closes, all paths adjacent to that barn also close and can no longer be used. That means that when one barn closes, we can't access it or the path that it basically connects to other barns. So, and then Farmer John is interested in knowing at each point in time, initially and after each closing, whether his farm is fully connected, meaning that it is possible to travel from any open barn to any other open barn along an appropriate series of paths. So fully connected just means that we can go from any barn to any other barn by traversing the paths that it connects with other barns. So this is going to be a bit hard to visualize until we draw it out. So we're going to do that later, but first we can check out the input and output format and try to make sense of that. But before that, so since Farmer John's farm is initially in somewhat a state of disrepair, it may not even start out fully connected. Okay, so this is a bit hard to visualize, but let's just read the input and output format first and see what we can do to make sense of it. Alright, so the first line of input contains N and M. So as you can see here, we have, in this case, N barns and three paths connecting these barns, so that's going to be M. Okay, so the next M line describes a path in terms of the pair of barns it connects. So here, as you can see, we have three lines that describe three paths. So as you can see here, this path is going to connect barns 1 and 2, 2 to 3, and so on. And barns are conveniently numbered 1 to n. So yeah, what I just said. This is going to be barn 1, barn 2, barn 3, barn 4. And the final n and lines gives a permutation of 1 to n describing the order in which the barns would be closed. Okay, so after this 3 m lines describe paths, these next last n lines are going to describe the order in which barns are going to be closed. So this is always going to be n long, and it's always going to be a permutation because he's going to eventually close every single barn. It just depends on what order it's going to be in. Okay, so now we have the sample input. We pretty much understand. This is pretty understandable and simple to visualize now. And let's see the output format here. So the output format consists of n lines, each containing yes or no. And the first line indicates whether the initial farm is fully connected. So this is the farm that has 0 barns closed down. And the line I plus 1 indicates whether the farm is fully connected after the ith closing. So again, we need to check whether the farm is initially fully connected because it might not be. You'd have some barns that have no paths connecting to each other, but once Farmer John starts closing these down, things might change. So we'll see. So first we can map this, just the sample input and output out onto a whiteboard here. So again, these barns and paths, this is just calling for a graph problem. So let's just draw each of these nodes for each barn, and let's draw out the paths as well. So we have 4 barns, and as you can see here, these barns are going to be numbered 1 to n. So draw 4 barns here. Please excuse my terrible drawing. There's some terrible circles. And 4. Alright, so we have 4 barns here, and you can see our paths are connecting 1 to 2, 2 to 3, and 3 to 4. So I think that should just make a circle where 1 and 4 aren't connected. So yeah, we have 1, 2 to 3, and 3 to 4. Alright, so there's our graph. And now we need to model how Farmer John is going to close these down and whether the farm is fully connected at each of these points. Alright, so Farmer John is going to, as you can see here, is going to close down farm 3 first. So we can just put an X over that. And now let's see, is the farm fully connected? Oh wait, actually first, let's just not do that. We have to first check whether the farm is initially fully connected. So before Farmer John closes any barns down, is the farm fully connected? Well, you can see here that we can indeed access any barn from any other barn using these paths. So we can go from 1 to 4, and that's going through each and every barn. So we can go from 1 to 2, 2 to 3, 3 to 4, and any other permutation of that. So yeah, yes, the farm initially is indeed fully connected. All right, so now we have to close barn 3 down. That's the first barn that Farmer John closes, and boom, barn 3 is now closed, and now we can check, is the barn fully connected? Well, we can go from 1 to 2, but we can't go from 2 to 4 because we have to go through barn 3, and barn 3 is closed. And as you know, when a barn closes, all paths adjacent to it also close and can no longer be used. So now the barn is not, or the farm is not fully connected. Yeah, gotta get my agrarian vocabulary in check. Alright, so now we can close, now Farmer John is going to close barn 4. So let's put an X for that. And now our farm only includes 2 barns, and so is this farm fully connected? Well, when you have 2 barns left, and these barns are connected by a bidirectional path. So yes, this farm with 3 and 4 closed is indeed fully connected. So we can put another yes. And if we go here, we have, next we close barn 1. And if we just close that down, well, now is the farm fully connected? Well, there's only 1 barn, and yeah, it's fully connected because it is fully connected within itself. We don't need to go anywhere else because there's only 1 barn. Can we access this barn? Yes, it's open. So yes, this farm with only one barn is fully connected. So yeah. So you can probably already tell. Oops, let me just redraw that so it's bigger. So you can probably already tell that when it gets to this last barn, it's always going to be fully connected. But we don't have to worry about that right now. We can worry about that when we start coding. So now that we have a pretty good visualization in how this problem works and we can understand how it works, we can start thinking about how we're going to put this into code. Okay, so since I know that this is the first time I'm addressing, I guess, this silver topic known as graph theory, I'm going to basically go over how we're going to approach this. So if you've never heard of this before, I totally understand, but just see if you can stick with me here. So the approach that we're going to solve this problem is called DFS, or depth first search, and basically in graph theory, that's where you basically traverse this graph in a way that allows you to solve a problem more efficiently. So depth first search is basically an algorithm for a graph. Let's just take this graph for example. This is not the graph in the problem, but for the sake of you guys understanding, it's just a 1, 2, 3, 4, 5 graph. And so the way depth first search works is that it always goes depth first. It's really basically what it sounds like. So it tries to go to the deepest possible branch of this graph first, and then it goes back to all the other ones. So the way that this one is going to work is that, as you can see, we have 5 nodes, and depth first search is going to start at node 1, and it's going to go 1 away to node 2, since this is the only direction it can possibly go. Now then, so now depth first search, since it always seeks depth, so it's going to go all the way down to, it's going to go through 3, then 4. So it's going to go all the way down to the deepest possible branch, or the most complex parts of this graph. And then after it's gone all the way to 4, it's going to backtrack and go back to node 5. So that's how depth first search works. It goes all the way to the deepest sections, and then comes back for the earlier ones. So it's like basically where you have like a tree branch here. It goes all the way to the end of the tree branch, and then it comes back to, let's just say these are like, this is just like an analogous sort of graph here. If you have like this super complex branch over here, it's going to go all the way to this one first, and it's going to come back and tackle these ones, and these ones, something like that. So yeah, that's how we're going to work. That's the algorithm basically we're going to implement into this code, so that we can, I guess, use this onto the graph we made over here. So as you know, this is the graph that we made earlier. Oops. create the check mark. So we're going to basically use DFS to basically depth first search these the barn or the farm graphs, and basically how that's going to work is that we're going to apply that on this, and depth first search. Depth first search is going to allow us to check whether each farm is fully connected or not each time. So, for example, if it can't possibly reach the deepest possible node, then that means the barn is probably not fully connected, because to be fully connected, all the nodes have to be connected to each other and accessible to each other. So that's how we're going to do it. Now, how do we actually implement a graph into code? Well, I created some slides here where basically you use something called an adjacency list. So an adjacency list is basically describes a graph into code form, and we can use it like a graph in our code. So basically, this is like an implementation how we're going to use it. So as you know, in the input format, they give us basically the path or a connection between two nodes is basically described by the two nodes that it connects. So the implementation we're going to use is listed here, where basically you use string tokenizer or whatever input line you guys use. But we're going to subtract 1 from its integer value because we're using 0 index, not 1 index. And then we're going to use something called an adjacency list, where it's basically an array list of arrays. And each array is going to describe the branches that it neighbors. So, and this is going to run in O n plus n time, because we have n nodes plus n branches. And how does this adjacency list actually look? Well, again, I told you that it was basically each node is represented by n minus 1 index because it's 0 indexed. And since this is an unweighted graph, where basically in a graph, you know that these paths can sometimes have values. Oops, it should be an arrow. Where these graphs just sometimes have values. So sometimes it could have like a 2 or 3 or a 2 again value. But in this case, we don't have any values. So since this is an unweighted graph, each part of the adjacency list is just going to describe the neighbors, not any values or anything. So as you can see, this is based on this input. This is how the adjacency list is basically going to look. So yeah. So now that we have basically oops, I should probably not say that many basicallys, but now that we have a basic understanding of our approach here, we can start basically implementing this into our code environment. So let's go. Alright guys, so I'm here with my IDE IntelliJ here, the one and only, and basically what I've done is I've read in the input using buffer reader and print writer, and I've stored it into some global variables and an m. And I've also declared my adjacency list, which again is an array list of integer arrays, and this is going to define which barns or nodes are neighboring which other barns and nodes. And like I defined on the slides, and here you can see I've used the same implementation for it as I put on the slides again. We read in 2 of the nodes that they give us. If we go back to USACO website here, if we go back to USACO website here, we can see that a path is defined by 2 nodes and the 2 nodes that it connects. So same thing here. A path is defined by 2 nodes to connect. We're going to 0 index them, and then we're going to store them into a adjacency list. And again, because these are bidirectional paths, we're going to store them for both A and B. And yeah, and as you can see here, I've declared a lot of global variables here. These 2 are just input and the adjacency list, but these 3 are the big ones. So visited, this Boolean array is going to allow us to check whether we have visited a node before in our DFS method. Count, that's going to help us check whether a barn is fully connected or not, because a fully connected farm, is only fully connected if all of the barns that are not closed are accessible to each other. So if we can count if we can count the amount of accessible barns, and if that count equals to amount of barns that Farmer John has not shut off or closed off, that means the barn is fully accessible, even though he already closed some. Sorry for this a bit stuttering over there. But next we have closed, which is basically going to check whether a barn has closed or not, because we need to start on a non-closed barn to start DFS, because we can't really start on a closed barn, because that would just like completely ruin the point, because we need to start on an open barn and see further from there we can access other open barns too in our DFS method. So yeah, sorry, I apparently I just can't English today. So yeah, from there let's start. Let's create our DFS method. Okay, so this is going to be a private static void DFS, and we're going to give it an integer. And what this integer is going to do is that it's basically the integer that we start DFS on. So it's basically the node or the number. The node, it's basically a node defined by this integer that we're going to start DFSing on. So we can use our visited Boolean array, and we're going to say, since we already visited this barn or node, we're going to say true. So we're going to set it to true, and from there we can increment our count because we've successfully visited a non-closed barn or node, and from there we can do our textbook DFS implementation, where we do our adjacency list here. Or you go through our adjacency list here, and we can say that if we've hasn't visited W and then we haven't closed this node, then we can recurse. And there you go. That's our that's our DFS implementation here. And okay, so now that we have our DFS implemented, so if you guys don't understand this, basically for every neighboring node, we can check whether they've been visited or not, and whether they're not closed or not. So if they haven't been visited and the barn has not been closed, then we DFS onto that node and we continue from there. So that's just how DFS works. Remember, DFS is depth first search, meaning that we always go for the deepest, most complex nodes first. So yeah, and now we can just continue with our general scope of our program here. So first we need to check. So let's see here. Okay, so we have our DFS method declared. So now we can just go through all of the nodes one by one through a loop and basically just check whether they're fully accessible and then print out the answers, and that should be the problem. Alright, so first we need to DFS the very first node, because first we need to check whether, sorry, not the first node, we need to check whether the initial barn is fully accessible or not by itself. Remember, because Farmer John is doing, what do they call it? Farmer John's farm is initially somewhat in a state of disrepair and may not even start out fully connected. So yeah, so let's just do that right now. So we DFS 0, and again, comments tell me to comment my code, so I'm going to do that. This is just a check if the initial graph is fully connected. Alright, I apologize for the loud keyboard, and next, after that, we have to arrays.fill visited false, because we need to reset this visited Boolean array for every time we run DFS. I can't spell. There we go. Alright, so now, how do we use our count variable to check whether it is fully accessible or not? Well, like I said, counts how many nodes we have visited that are not closed, and basically it's going to allow us to check whether it's fully accessible or not. So how is it fully accessible? Well, that means that all of the nodes are equally accessible to each other. So that means we have to check whether count equals n, or how many nodes there are, because in the beginning, no nodes are closed. And right now when I'm saying node, I just mean barn, because I guess node is just vocabulary that I'm used to with graphs. So yeah, p.print n and else, p.print no. Alright, so that just checks whether the first farm that is not touched, the initial farm that is untouched by Farmer John and has no closed barns, is fully accessible or not, or fully connected, whatever they call it. Alright, so
Now let's declare our int p, or just a variable to increment throughout all of the nodes, the remaining nodes. I mean, all the remaining times that Farmer John closes a barn. And now, now we can just declare a for loop here, and let's see here. How big does this have to? Okay. So, all right, start from here. All right, let's see here. I think it's gonna have to start from 1. Okay. So yeah, this loop is going to start from 1, and it's going to go all the way until n. Hold on a second here. All right, there you go. All right, so why does it start from? Oops, I think no, we're good. Okay, so I is going to start with 1 because again we already processed the first time that we check whether it's fully connected or not. So it's going to start from 1. Yeah, sorry about that. It took me a while to think that out. So now we can declare a variable that's going to allow us to check whether all right. So this variable is going to read in our the node that we're going to close, or Farmer John is going to close. So yeah. So in close is going to equal to that, and then from there, we can say close minus 1 because we're 0 indexing it equals to true. So what are we doing here? So again, we have a global closed Boolean array, and this is going to say which nodes are closed and which nodes are not closed. So if closed equals to true, so again, we read in the initial, we read in the node that Farmer John is going to close, and then we put that into code form by using our closed Boolean array, and here we 0 index it, so it's going to be 1 less than its index. We can again index starts at 0, and from there we can because we need to start DFS from a non-closed node, we need to look for a non-closed node if this one is already closed. So p++. So we need to look for a non-closed node to start DFS. So how do we do that? Well, we can use a while loop, and for every closed node, we have to go check the next one if it's not closed. And once we reach a node that hasn't been closed, we can start DFS. So first, we need to reset our visited array. So false. We can also need to reset our count here. And now we can just do DFS for our p value, which increments throughout all the nodes. And from there, count gets affected because again, count is going to count up how many nodes that we have traveled to using DFS. And we can say equals n minus I. And pw.print on yes. And else pw.println no. So again, if a barn is fully connected, we say yes, else no. So you might be confused, why is this n minus I? Well, let's just say that Farmer John has closed 1 node, and that remains 3 nodes. And if those 3 nodes are fully connected, meaning that we can traverse through all the 3 nodes, that means the barn is fully connected, but it's still not 4 nodes like the original because he closed 1. That means we have to subtract our I value because 1 node has been closed, and we can't consider that to whether the barn is or the farm is fully connected. So yeah. Now we can just finish up our p by resetting it over here, and then from there, our loop will reiterate again and again. And now we can just finish up the problem by just saying pw.close and br.close because all of our work has been done by the loop above. So yeah, that pretty much finishes this problem. Alright, so now this problem has pretty much been done.
I'll scroll through it one last time in case you guys need it. You can pause the video as you need. So this is just the input, and then we process the first time the initial farm and see whether it's fully connected. Then we go through all the nodes once Farmer John starts closing them, and there's our DFS function. Yeah, pretty solid problem, I would say. With DFS knowledge, it's not that bad, I would say. So yeah, let's just get this plugged in into our online grade server and see how we do. Alright guys, I'm here at the USACO website, and I have my file plugged in, and it's go time, boys. Let's submit it. Alright, see how we do. Grading in progress. That's good to see. Okay, 1. Come on, all green, all green. Gotta see that all green. And let's go. Let's go. Alright, 10 test cases in the bag. That's it, boys. We've done it. Alright, so this has been a blast. 2021, this channel has pretty much exploded, and I can't thank you guys enough for that. I hope you guys enjoyed today's video, and I'll see you in the next episode, which is going to be in 2022. Hoping for big growth, and even if it's just a little growth, I just want to see growth in 2022. And I think, again, it's all up to you guys. You guys mean the world to me. So yeah, thank you guys so much for watching. I'll see you in the next video. Bye.